Imagine throwing a tennis ball at a solid brick wall. In the classical world, it bounces back. But in the quantum world, particles don't have to bounce. A particle can hit that exact same barrier and pop out on the other side. For decades, this left us with an awkward question. What exactly is the object physically doing during the exact moment it's trapped inside that solid atomic barrier? The standard assumption in physics was that there wasn't an inside to worry about. We treated the whole event like a glitch in the matrix, assuming the electrons teleported across these energy gaps instantaneously. Treating a primary atomic process as magic creates a massive gap in our knowledge. Our complete ignorance of what happens inside the quantum wall has become a strict limit on our ability to advance modern physics. Instead of just vanishing and reappearing, electrons actively bounce and surf laser energy while trapped inside the barrier. To track this, you have to measure time on a mind-bending scale. Researchers are now tracking movements in attoseconds, a billionth of a second. Engineering hyper-fast processors or next-generation atomic materials requires mapping this exact attosecond scale journey inside the wall. To understand why this bouncing behavior was hidden for so long, we have to look at how physicists usually explain light hitting an atom. The first classic view is the ladder model. An electron absorbs packets of light, using them as literal steps to climb vertically out of the atom's pull. Then there is the crushed wall model. If you fire an ultra-strong laser at the atom, the sheer force of the electric field physically flattens the energy barrier, allowing the electron to simply slide out horizontally. But real-world lab experiments usually rely on medium-intensity pulsing lasers. They sit in a messy middle ground where electrons emerge carrying impossibly high amounts of energy that neither model can explain. The electron isn't climbing high enough to explain the boost, and the wall isn't flattened completely. This means physics requires a new framework to explain why these electrons are emerging with such high energy levels. This framework is the under-the-barrier recollision model, or UBR. It maps exactly how those electrons pull off their high-energy escape. First, the incoming laser pulse hits the atom and slightly bends the atomic wall. This brief distortion creates an opening, and the electron steps directly into the darkened zone of the barrier to begin tunneling. But the laser isn't a steady beam, it's a rapidly oscillating pulse. As the wave flips direction, the barrier shifts back, and the electron ricochets off the inside geometry of the wall. During this trapped ricochet, the electron is continuously bathed in the laser's field. It absorbs massive amounts of energy while locked inside the wall, before finally breaking through to the other side. Right before its final escape, this intense energy injection forces the electron into what physicists call a Rydberg state, a highly charged temporary holding pattern. The electron takes a distinct, measurable, geometric path, following a precise physical trajectory rather than an instantaneous, unexplainable teleportation. By tracking this hidden ricochet, the math suddenly balances. This specific mechanism finally explains exactly where that extra energy originates. To prove this was real, researchers fired 30 femtosecond laser pulses into a cloud of xenon gas, carefully tracking the energy and momentum of the ejected electrons. According to the old teleportation theories, the number of high-energy electrons you catch on the sensor should drop sharply as you increase the laser's intensity. This heat map shows the actual results. Instead of a drop, you see prominent horizontal green and red fringes cutting across the diagonal lines. These are Freeman resonances. Their horizontal path indicates high-energy electrons keep flying out at a continuous rate, regardless of laser intensity. This chart shows the exact same measurements run on krypton gas. This confirms the phenomenon as a universal rule rather than a quirk of xenon gas. These highly specific, flat spectrographic lines provide the physical evidence that under-the-barrier recollision is a reality. The researchers note that while this math perfectly simulates noble gases like xenon, the calculations become chaotic when applied to multi-electron molecules that push and shove each other. However, by understanding the timing of this ricochet, we can start using lasers to steer individual electrons and physically snap chemical bonds in real time. In the next decade, this leads toward light-wave electronics, computer processors powered by guided light pulses that operate millions of times faster than current hardware. This evidence shows quantum tunneling is a physical, timed sequence occurring inside the wall, where electrons follow a choreographed path of energy absorption. The UBR model transforms the once impenetrable barrier into a predictable environment, allowing us to guide electrons with the precision required for light-speed hardware.